For part A of this problem, we're trying to find the total time it takes for car A to travel 15 meters. Now, in this particular case, there's actually two types of motion that car A experiences. For the first certain amount of time, which we don't necessarily know yet, it accelerates at 1.5 meters per second up till it gets to a speed of 5 meters per second. And then after that, it continues moving at a constant velocity or constant speed. So really, we have to break this down into two parts. So first, what I'm going to do is I'm going to find how long it takes to travel whatever distance to get to a speed of 5 meters per second. So it starts off moving already initially at 2 meters per second, accelerates at 1.5 meters per second squared, reaches a final velocity of 5 meters per second, and that actually comes out to a time of 2 seconds. So that's part of the problem. Now, we have to also take into account during that time it traveled some distance which we don't necessarily know yet. To figure out the total time, we need to know how much further it still has to go to reach car B. So we use that time to figure out how far it traveled for that first 2 seconds, and it turns out it traveled 7 meters during that time. So that means that there are 8 meters left to add up to a total of 15. So for those last 8 meters, again, it's moving at a constant speed, so distance equals speed times time, 8 meters at 5 meters per second, and that is 1.6 seconds. So 2 seconds for its acceleration, 1.6 seconds for the constant speed, giving us a total time of 3.6 seconds. Now, the two collide with each other, and we want to know, after the collision, we want to know the impulse felt by car B. Now, we know that car B starts at rest. Impulse is simply just a change in momentum, so mass times the change in velocity of car B. We're only looking at car B right now. So its mass is 200 kilograms. Its final velocity to the right at 4.8 meters per second, minus 0 because, again, it was at rest, and we get 960 newton seconds. For part 2 of B, we want to find the speed of car A after the collision. So this is a conservation of momentum problem. Anytime you're dealing with collision, you should be thinking conservation of momentum. We know that initially the only thing that is moving is the 250 kilogram car A at 5 meters per second immediately before the collision. So that's the initial momentum. And then after the collision, we know that the 200 kilogram mass moves at 4.8. So we set it up, do a little bit of algebra, and we see that the velocity of car A is 1.16 meters per second. Now, I drew a little arrow there to the right because I know it's still moving to the right because the number came out to be positive. If it came out negative, that's totally fine. That's acceptable. Velocity is a vector. It can be negative. That would just mean that it's going now in the opposite direction. So it would be going to the left, but it's not. That actually leads us to the next point, part 3. Kind of just answer that question. Car A after the collision, because the velocity ends up positive. That's really the only way we know that it is still, in fact, moving to the right. Now, for part C, the very last part here, is this 100% or perfectly elastic? When we talk about elastic collisions, you always got to be careful. There's, again, when we talk about elasticity, it's a very gray area. Something can be 0% elastic, meaning they completely stick together, or it can be 100% elastic, meaning completely bounces off and all the energy is conserved. And there's gray in between. It could be, maybe 80% elastic, in which case energy is not conserved. So we got to look at energy before, energy after, specifically kinetic. So initially, 1/2 mv squared of car A, that's the only thing that's moving, equals 1/2 mv squared of car A plus 1/2 mv squared of car B, knowing the masses and knowing now the final velocities. And we see that the two sides of the equation do not equal each other, meaning there is energy lost in this collision. So therefore, technically, even though they bounce off each other, the energy is technically inelastic because it is not 100% elastic. So we're going to say no.